Let's take a look at question 703 on Leet Code, the kth largest element in a stream. And this question is a perfect example of why data structures are important, because this seemingly simple algorithm to solve, if you solve it in the intuitive approach, you end up with a really bad time complexity. Whereas if you just know the right data structure to use, and in this case, it's going to be a stacked data structure, which we talked about in the previous video, that will significantly improve the time complexity. And there's also a little trick. So let's take a look at the question. We need to design a class to find the kth largest element in a stream. So we're just looking for the kth largest number in an array of numbers. So if it's the first largest number, it's the biggest number in the array of numbers. If it's the second largest, it's the second largest number in the array of numbers, and so on. And we're going to have the parameter k, which we're going to have the argument passed in. So we need to allow for that. And then there's this note that it is the kth largest element in the sorted order, not the kth distinct element. So we need to implement the kth largest class. And we see that it takes the k, which is the number corresponding to the position of the largest element, so 1, 2, 3, and so on. And then we have the numbers. So basically we're going to have this add method here, and this is going to append an integer to our array of numbers. And then it's also, in addition to adding the number to our array, we're also going to return that element representing the kth largest element in the stream. So let's just have a look at an example just to clarify what's going on. So you have a class called the kth largest, and you initialize that, and then you pass in 3. So you want to get the third largest number here. So here we've got the numbers 2, 4, 5, and 8. So the third largest here would be the 4. So essentially, if we add an element, we're adding 3 to this list. So 3 is still smaller than the 4, so the 4 will still be the third largest element in that list there. So, and of course, if you add more and more, it will pick out the third largest with the new numbers in the array there. So that's what we're trying to do here. So let's just take a look at the intuitive approach here. And this is what you get to start off with in the code here. You just get this empty constructor with the arguments k and nums, and then you have this add function here. So the intuitive approach would be to sort the numbers and then return the position, the index of the sorted array, if they're sorted in descending order. So for an example, if you make k equal to the number, and then we'll just equal on the class, we'll have these properties number, just so it makes it simple to assign things. Basically, in our constructor, what we can do is we can just set this dot k equal to k, and this dot nums equal to nums. And then basically we could solve this pretty quickly just by saying, well, we just want to take the nums and we want to push to it. And then what we would want to do is we want to get the sorted nums, and we want to get that in descending order. So I might just put that in the name there. And we can do that just by sorting. So JavaScript has the sort method built in. And to sort it in descending order, we take the second number, b, and subtract a. If we wanted ascending, we'd go a minus b, but we want descending order. So largest to smallest. And then basically we'll just want to return that sorted array here, and we would want to just put in the position k, which we have access to with this k, and we'll just subtract 1 from it. So that's all well and good. It will run, but it's quite inefficient. And we need to think about why this is inefficient. And this will help us choose the correct data structure for this problem. So the reason that this is inefficient is because every single time you add a number, you need to do this sorting. So you need to, and sort is a n log of n operation. So it's actually not too bad in itself, but you need to consider that we're adding many numbers. So each time it's n log of n. Now, if you watch the previous video, which is pretty much mandatory to understand this video, we talked about the stack data structure. And when we insert into a stack is just a binary tree. So if you want to insert something or remove something, but we're thinking about inserting here, you need to go to the final, the child of the branch, and you need to insert something there. And you can actually perform that in log of n time complexity rather than this n log of n time complexity. So it's much better considering add's going to be the main function that we're using here. So to do that though, we need to have our data structure. And this is why it's important to watch the previous video, because in this video, we're going to build up on the data structure that we've got here. So you can see that we've got this min heap class here. And if you're not sure where this came from, make sure you check out the previous video because we implemented this in the previous video. The only difference is this time we have specifically a min heap, whereas another one we had a min heap which extended a heap. So I just renamed the class here to min heap. And then I just put the compare function directly here. And then I've got this get min value function here instead of get peak top. And then all the rest of the methods, they're going to be the exact same. So we have insert, heapify, swap, and then we have all of our helpers to get the parent index, left child index, right child index, has parent, left child, right child. Now this might seem like we're writing quite a lot of code, but it turns out the code's much more efficient. So even that's a trade-off you need to make is, if you're writing an application, do you want to have the simple approach where you have nice readable code, like this is pretty lean, but the performance might be important. So you need to actually, sometimes writing more lines of code is actually better. And in the case of data structures and algorithms, it most certainly is. But this is actually kind of a cool question because you might start thinking like, why are we using a min heap and not a max heap? Because we want to get the kth largest number. So wouldn't it make more sense to get the max heap? And there's a couple of reasons. The first reason is, and this is like the trick to the question, to be able to solving it efficiently, is if you use a minimum heap, and you have the numbers 1, 2, and 3, and then let's say you want the third largest number, the third largest number is going to be at the top of the heap. So you can just do an O of 1 lookup to look at the very top there. Now, you could have, say you had 5 elements in your array. Like how would you know, if they're ordered or not? And basically, we want to, since we have a heap, and with the heapify method, we know that our array is going to be structured in a heap. So what we can do is, let's say we had 5 elements in our array, but we only want the third largest. The reason the 4th and the 5th won't be, or the 5th won't be on the top there, and I should say smallest, is because before we don't actually put it into the heap. Since everything's sort of heapified before, we can actually pop from the heap, remove the numbers. So let's say we have numbers 1, 2, 3, 4, 5. We want the third largest number. We could, in that case, we could remove the numbers 5 and 4. Oh, sorry, and when I'm saying numbers, I mean indexes. So 3 and 4. they'll cut out the elements, and then the min heap, the top element will have the the third or the kth largest. So and we'll see this in the code. This will probably become clearer as we go on. So let's just write this up. So I'm just going to get rid of this nums here and this code in here. And actually, since we just were talking about popping from the heap, let's just go ahead and write that method up, because I think that'll help illustrate what we're actually doing here. So we have the public method, and we're going to call it heap pop, and it's going to be slightly different to pop in the sense that pop, you'd be removing the last element, but this one we're removing it and heapifying things. So basically what we can say here is we can say, well, this heap array here, if it has a length of 0, we simply just return undefined. This is just if the heap is empty. This should be if, sorry. So basically we want to look at the, and if you have to see the heap video that I created to understand how we go about swapping things and stuff like that. So basically we just take the root value here and we take the heap array, and then we take the smallest number in the case of a min heap. So, and basically we want to get the last value as well, which is going to be the heap array pop. This is going to be a number, just to ensure that it's there, sort of thing. We want to remove that last element. And then what we want to do is we want to take the heap array, and if it has a length greater than 0, what we want to do is we want to say, okay, well, we want to get the heap array in that first position there, and we want to set that equal to the last value. So we've just swapped the last value with the first value, and then we can call heapify on that first value. So that will heapify the entire tree, meaning the array. So everything will be in accordance to the heap property. So we reheapify the heap from the root there. So we're going to have this, and we're going to see how this comes into play in a moment. So basically we've just and we need to return the root value here. So basically all we've done is we've just popped the last element from an array, we swapped it with the root, and then we've called heapify on the root, which will heapify the array for us. So now we can actually look at the code, and since we have this min heap class, it actually simplifies the code for us, because we don't have to re-implement things, although we've already implemented in the previous video. So basically what we want to do is we want to make use of our min heap data structure, and we can initialize this to the minimum heap here, and then we can just say we can have a for of loop. So for the number of the numbers that we get passed in here, we can simply say min heap dot insert the number. So this is just taking the array of numbers and then putting them to a heap, and the insert method makes sure that the heap property is satisfied. So one thing to note though is we don't need extra numbers, right? So what we can say is we can say while this dot min heap dot length, and we might need to create a length function here. So I'm just going to have length, which is going to give back a number, and we're just going to return this dot heap array dot length, length like this. So now we have the length there. We can utilize the length of the min heap. So that's just getting the length of the array. But since it's an object, we need to do it with the method length here. And if that's greater than k, what we need to do is we need to take our min heap, and then we need to call the heap pop method that we just created here. So hopefully that's clear while we're doing that. Perhaps I'll just reiterate over that once again, now that we can see the code here in front of us. Essentially, what we're doing here, let's say we just have an array 1, 2, 3, 4, 5, and we want to get the third largest number. So k is equal to 3, and then we have these numbers here. 1, 2, 3, 4, 5. We want to get this number here. But basically what we want to do, and this is sorted in a heap, because you've got to imagine the root node's 1, then the left child of the root's 2, the right child's 3, and then the left child of 2 is 4, and the right child would be 5. These 5 and 4, they could be switched over. There's no guarantee that they're you know, the right child's bigger than the left child, for example, in the heap, because the heap property just says that the child has to, in the case of a min heap, has to be greater than or equal to the parent. And, you know, similarly for a max heap, it would be the other way on. But we're considering a minimum heap. So basically what we want to do is, since we're using a minimum heap, we're able to pop off the end of the array, and then we're able to look up the beginning of the array in O of 1 time complexity. So, and we can insert in log of n, which is much better than the n log of n. So, you know, that's why the heap data structure is so efficient for us in comparison to the more simple intuitive approach. So what we're doing is to be able to put that into the heap. So if we want the third largest number, we want to take these three numbers, and then the minimum heap, because you've got a heap, the third largest number will be this one at the top there. So I hope that makes sense. If it doesn't, just draw it out on a tree, and hopefully that will make sense to you. But to be able to do that, we want a heap of just these three numbers, which means we want to pop these two out of the way, because if, you know, they might get in the way, sort of thing. So, okay. So with that in mind, we can create our add function. And this is going to be quite straightforward now that we understand the intuition behind why we're solving the problem. So basically we can just take this min heap that we have on this class here, and we can call the insert method, which we've previously created, which is a log of n operation here. And that's a capital H. So basically, if this min heap has a length greater than this dot k, what we can say is this dot min heap dot heap pop. Because let's just say, let's go over this one more time, but from this add perspective, if we have the numbers 1, 2, and 3, then we add the number 4. Basically, we need to insert the number 4, and then inserting the number 4, because this number could be 1 or something else. And when you insert it, that's the log of n, because it goes to the end of the branch, which is the height of a binary tree, which, you know, subdivides by 2, so that's the log of n, or log base 2. And if that's greater than k, so let's say k is 3 here, and we've got 4 elements, 4 is greater than 3. So we need to, and let's use number 4, that looks easier to understand because it's larger. We can simply just pop this number off here. And then, you know, when we go to look at our first element, it will have this 1 here. So we call this min heap.heap pop. And then what we can do is we can just go ahead and this add function, it's sort of overloaded because it does this insertion. It also does this popping and then getting the min value all in one function, but that's what the question wants. So let's just go ahead and return this dot min heap dot get min value here. And let's just go ahead and see if that works. So let's just go ahead and submit the code here. And we can see it beats 86%, which is much better than what it was. I checked before on the first approach, I think it was beating 20%. So we can really see how this stacked data structure can significantly improve our time efficiency. So thanks so much for watching, and I'll see you in the next video. Cheers.